Okay, so I'm going to talk now about distributed consensus and how this is used in Bitcoin. What is a consensus protocol? A consensus protocol is like a set of rules that different computers, network computers, can use to talk to each other, and what they do is they send messages so they can come to agreement on some value. I think it's pretty useful when we talk about these kind of things to have like a nice kind of relatable sort of real-world model or metaphor. And one of the kind of most famous ones is this thing called the Byzantine generals problem, which was proposed first by Leslie Lamport, Robert Shostak, and Marcel Peace in 1982. And this guy, Leslie Lamport, he comes up all over the place in distributed systems. He's really a master, actually. So the problem is that all of this is the Byzantine generals, they all come together and they're surrounding a castle. They've just arrived at the castle and they're all in separate camps, and they have to look at the castle and they have to decide, do we attack the castle or do we retreat? Because they have to see, do we have enough like forces or power to attack the castle? I don't know. And the way that they do this is they have to send messages to each other. So they're all in different camps and they have to send messages between the camps. Maybe they're sending messengers on horses between the camps. What's important is they must agree, all of them together, either to attack or retreat. If half of them attack and half of them retreat, then the ones that attack will die because they don't have enough power to overcome the castle. And on the face of it, this doesn't seem like such a difficult problem to solve that, you know, you could imagine that, okay, all of the generals write down their vote, do we attack or do we retreat? And then they send it to all of the other generals, and then when each general receives all of the votes, okay, they decide, do we attack or do we retreat? But what makes it difficult is, first of all, maybe the messages get lost between the camps, or I don't know, the enemies in the castle like assassinate them, and maybe the generals also get assassinated. This would be like the computer crashes, because the generals are actually computers and the messengers are network links. So suddenly maybe all of the messages aren't getting through, or one general only sends half of the messages and then doesn't have time to send all of them because he gets assassinated or the computer crashed, you know, like, and then what makes this specific formulation of the consensus problem, the Byzantine generals problem, even more tricky is that some of the generals can be traitors, they can be malicious, and so they're trying to craft specific messages or a sequence of messages to disrupt the consensus protocol. So their aim is to either make it so everyone gets confused, we don't reach agreement, people think they've agreed, but they've actually got confused, half attack, half retreat, or the other thing is they trick everyone into making a different decision than they would have made if there wasn't a traitorous general. And so they can even do that, they can even send different messages to different people. They could say to half of the generals, hey, attack, and half retreat. And once you have this kind of real tough formulation of the problem, you can see this kind of simple voting protocol just really is not going to work. And this is like a really important kind of problem of computer science. And what makes like a good consensus protocol is we want two things. The first is we want this property called liveness. So that's all of the participants eventually decide on a value, like no one gets stuck. So if a computer crashes, the protocol will continue. It can tolerate a certain number of failures. And the other thing is safety, which is this property that all of the participants decide on the same value. So all the generals either decide to attack or retreat. And so we want liveness and safety. This is a good protocol. And to make that more kind of concrete, what is the actual use in a computer system of consensus? It's not just for generals attacking castles, it's also used as this kind of pattern called state machine replication. And you can imagine that, okay, if I'm running a website and I have my database server, and this is like really important, you know, if the server catches fire or crashes, and then the database isn't working, and then my website's down, and then that's really bad, because especially if it's, you know, it's a big website, and this is serving like a lot of traffic. If the website's down for 10 minutes, could be already millions of dollars. Like we really can't tolerate even a second of downtime. This is what we're aiming for. And so to achieve this, you have replicas where you have multiple copies of the same database. You split it up, and each one always stays in sync. And then so if one database catches fire, it's fine, you still have the other two, the website keeps going, everyone's happy. And to achieve this, we model each database as a state machine. And what is a state machine? This is a finite state machine, slightly simplified, but basically you have states, and then you have inputs, and then you have this thing, the state transition function. And so we take inputs and states, and then we transition to the next state. So we start in one state, we have process a set of inputs, we move to the next state. And this just continues. And what's important is that this is like a completely deterministic process. So given one state and one set of inputs, the same state and the same input, every single time you run the function, you're going to transition to exactly the same state. So this is a totally deterministic thing. And then we imagine that, okay, each one of our database replicas is a state machine. And then what we need to do is we need to define how do we keep all of these replicas in sync. And the way we do that is we use consensus. So this is the protocol. This is the consensus protocol. Up here in the top, we have all of the requests from the clients. And all of the database replicas have to talk to each other and decide in which order do we process these requests from the client. So they run one round of the consensus protocol and they decide, okay, this is the next message. And then they decide again, and this is the next message. And so what they do is they use the consensus protocol to define a consistent ordering of the messages. And so once you have every single replica has exactly the same ordering of the messages, then you know that if they all process these same messages in the same way, in the same order, because they're completely deterministic, all of the states are going to advance in lockstep, and everything's going to stay together, and they're going to be consistent. And so this is kind of the classic primary use case for consensus protocols in distributed systems. And this also is pretty much exactly what a blockchain is. Actually, it's not so different from this. Kind of a brief history tour of some famous consensus protocols. Again, here is Leslie Lamport. Paxos in 1989 is probably the most well-known consensus protocol, and here we can tolerate a certain number of nodes crashing. We can't tolerate these Byzantine failures, so that we can't tolerate traitors. So this if we're kind of thinking about what is the model of Paxos, we think, okay, this is my data center, I control all of the nodes, I trust all of the nodes, but some of them are going to crash, and so I need my protocol to be tolerant of crashing nodes and also delayed or lost messages. And the other important thing is that this consensus protocol has a closed membership. So I have to talk to some central authority to say, okay, can I participate in consensus? There is someone who has a list of all of the nodes who are participating in the consensus protocol. And then in here, like 1999, comes PBFT, which is Practical Byzantine Fault Tolerance. And this is Barbara Liskov and I think Robert Castro? I forgot, sorry. 1999. And so here, this is the first kind of really usable protocol that can tolerate Byzantine faults. We still have the same network model, delayed and lost messages, and we still have the closed membership. And so this is the kind of protocol that people use in like these private or permissioned blockchains, enterprise blockchains, like Tendermint is actually just a deployment of PBFT. And then finally in 2008, we have this Nakamoto consensus from the wonderful Satoshi Nakamoto. This is the consensus protocol of Bitcoin, and this is kind of the key innovation of Bitcoin actually was a novel solution to the consensus problem. And here we have the same, we can tolerate Byzantine faults, we can tolerate delayed or lost messages, and also we have, for the first time, we have open membership. So now anyone can join the consensus protocol at any time, anyone can join or leave. There's no, it's permissionless. Like I could come here, I could start my command line, I could start running Bitcoin D, and I could join the consensus process right away. So no one can control who is part of the protocol. And that's obviously like a pretty difficult problem to solve if we think about the generals that, the generals are joining and leaving all of the time, and also if you have like a malicious attacker, they could really just overwhelm you very easily by maybe spinning up 1 million nodes on AWS. And then they have more than half of the votes, and then you're done. You can't tolerate that much failure. And so the way that this is kind of dealt with is that you change a little bit what one vote means. In previous protocols, you would say each computer has a vote, so that's like one IP address per vote, whereas with Nakamoto consensus, it's rather the influence you have over the process of consensus is proportional to how much CPU power you have. So that actually makes it much more expensive to gain more influence over the consensus process. And the other thing with the big innovation is that you have good behavior rewarded with financial incentives. So you add this layer of financial incentives over the top of the consensus process, and this is how you have this like open, permissionless, distributed system. So that was kind of high-level theory. Bitcoin is, what is it? Actually, it's like a public, immutable, ordered list of transactions. And so public means anyone can see it. Immutable means it can never change. Once you've added something to this list of transactions, you can't be removed, it can't be replaced, and you can only add things to the end. You can't add something to, for example, the middle. It's ordered. So this is, again, this. If we think of the state machine replication, we're defining an ordered list of inputs. This is it. It's very important that we have this ordering. This is the whole kind of point of the consensus process. And yeah, a transaction, this is just the input, and really this is representing a transfer of value. Like I'm sending 5 Bitcoins from me to Bruno. This is a transaction. And what does this look like? It's a global peer-to-peer network. There's 3 kinds of nodes. There's like a full node, and a light client, and a miner. And the full nodes and the light clients we're not going to worry too much about today, but that's basically people who are just sending and receiving transactions. They're not participating in the consensus process. And the difference is that a full node stores a list of all of the transactions, whereas a light client stores a much smaller kind of piece of data, just the headers of the block. So this is something you could run on a phone. But yes, so this is what we care about, the miners. And these are the miners, and these are the ones that participate in consensus. And so that's what they're doing, is they're all talking to each other, and they're agreeing what is the next transaction that's going to go on the ledger. And so what does it look like? The data. To talk about that, first need to talk about 2 kind of fundamental cryptographic primitives. The first one is a hash function. And so this is a one-way function. So a hash function, you put in some data, and you get a unique identifier for that data out. What's very important is that if you put in a different piece of data, you get a completely different output. So this uniquely identifies data. And the other really important property is that if you have the output of the hash function, you can't infer the input. The only way you can figure out what the input to the hash function is by trying every possible input until you find the output that you were looking for. So and the output space, the space you have to search through, that is so large that it would take until like longer than the heat death of the universe to effectively reverse a hash function, right, given current computing resources. Yeah, and what do we use this for? First, to uniquely identify messages. And the second thing that's interesting is this also we use to prove an ordering. So if I have 2 messages, I have message A and I have message B. If message B contains a hash of message A, then because you can't reverse the hash function, you can prove, cryptographically, you can prove that message B must have been created after message A, because the only way you could add the hash is by knowing what message A is. And so this we also use to impose an ordering, or to prove an ordering. The next thing is digital signatures. And so this uses asymmetric cryptography. And so in asymmetric cryptography, you first choose a random number. This is your private key. And then from the random number, you put this through a one-way function, which is the same property as the hash function. You can't figure out the private key if you know someone's public key. So you take the random number, you put it through the one-way function, and you get a public key. And then the public key I distribute widely. This like represents my identity in the world, basically. And using this key pair, I can do a few things. One of them, and the one that we're going to use in Bitcoin, is I can create a signature. So I take the message that I want to send to someone, and I take the private key, I combine them, and I produce a thing called a signature. And then I send the signature together with my message. And then once I have the signature and the message, and you receive, I send you the signature and the message, you receive the signature and the message, and then you can verify the message using the public key, the signature, and the message. And by verifying it, you prove 2 things. You prove, first of all, that the message was sent by me, or sent by the person who controls the corresponding private key. And the second thing is you prove message integrity. So you prove that the message wasn't changed in transit. So if I send you the message over the open internet, I don't trust all of the nodes that it's going through, but if I send it with a signature, you can know that this is the message I wrote and sent to you originally. So this is transactions. This is the kind of the fundamental structure of Bitcoin. Transactions have inputs, and transactions have outputs. Outputs have amounts, so they have a value, and inputs consume outputs of previous transactions. So an output can only be consumed once, and you can really think of an output as a coin. This is like, it can only have one owner, it can only be spent once. If I want to split an output, I have to make a new transaction that splits it into 2 different outputs. So you can see here I have 5, and I want to split it into 3 and 2. I must make a transaction with 2 outputs. So here we have this kind of linked chain of transactions. And this is what it actually looks like on disk. So here you have an array of inputs, and you have an array of outputs. The inputs refers to an output, first by the hash. So we look up the previous output that we're consuming by hash, and then we also provide the index in the output array. And the other thing is we provide a signature, because the outputs have an amount, and they are locked to a public key. So you can't spend an output unless you provide the signature that proves that you control that output. Because I have the public key, I have the signature, and the message that I sign is the entire transaction, I can prove cryptographically, if I send someone a transaction, whether or not I had control of that output, whether I had the corresponding private key for the public key that locks the output. This is actually implemented with a kind of a simple scripting language in Bitcoin. So rather than you have an unlocking script and a locking script, and then when you're verifying the transactions, you take the unlocking script, and then you append the locking script, and then you run it all the way through. If it's true, the transaction is valid. If the output of the script is true, the transaction is valid. If the output of the script is false, then the transaction is not valid, and it will be rejected by the network. And so already in this, you can't spend money that doesn't belong to you. You can only spend money where you control the private key. And this transaction structure would already be enough to work with Bitcoin. We could just run the consensus protocol and choose an ordering of single transactions, but consensus is a very slow thing. So what we do is we batch the transactions up into a block. And a block has two parts. It has a header, and then it has the data. And there's a lot more transactions than this per block. There's like 1,000, roughly, transactions per block. And in the block header, there's two things. First of all, there's a hash of the previous block. And then the other thing is there's a thing called a Merkle root, which is the root of a structure called a Merkle tree, which is an interesting structure, but not super relevant just for the consensus process. So for now, you can really think it's just a hash. If you're interested, definitely look up Merkle trees. They're great. And here you see, again, we have an ordering. We use the hashes to impose an ordering, and each block encodes not just the previous block, but in fact, because the previous block header includes the hash of the previous block header, which includes the hash of the previous block header, each block encodes the entire structure of the blockchain all the way until the very first block. And so the block is only valid if it's exactly that chain underneath it. And this is useful because we have this cryptographically verifiable structure. We can verify data. If I'm a node that just joins the network, the only thing I have is this first block with the genesis block. And when I join the network, I only have this, and I talk to my peers, I connect to my peers, and I say, hey, please provide me with some data. Please provide me with the blockchain, in fact. And so I request the first block, and I can check. I can say, oh, do the signatures all match up? Do the hashes all line up? And if it does, then it's valid, and I accept it. And I keep doing this. But if someone sends me a block that's not valid, that's not like a block that matches this blockchain, then I can reject it straight away. If the inputs don't line up, or the signatures don't line up, or the hashes are all wrong, then I can just reject it. So as a node joining the network, I don't really have to trust. I trust a little bit, but I don't have to trust too much, excuse me. And so that's the data. That's what the data looks like. But what is this process of consensus? This is Nakamoto consensus. How does this work? Here we have the miners, and what the miners are doing is they're all racing to solve a difficult cryptographic puzzle. First of all, they have all of the unconfirmed transactions, so that's a transaction that hasn't been included in a block yet, and they take the transactions and they build a potential block. And then they race to solve a cryptographic puzzle. And the first one that solves the puzzle commits the solution to the puzzle into the block, and then sends this out to their neighbors. And the neighbors can, again, they can verify all of the data. So they can look, and they can even verify that the solution of the puzzle is correct. And so if the block is correct, if it follows all of the rules of the consensus process, they add it to the end of their chain, and then they start working on the next block. So they have the unconfirmed transactions, they do a potential block, they find the puzzle, and maybe a different node finds the puzzle this time. What's important is that it's kind of random, it's proportional. So if you have more CPU power, you're going to find a solution to the puzzle more often. If I have 20% of the CPU power in the network, I'm going to find a solution to the puzzle 20% of the time. And then they broadcast it to their neighbors. What does this puzzle look like? This puzzle is the proof of work. And so this is the fields in the block header. We have the previous hash, we have the Merkle root, there's also just a hash of all the transaction data, and then we have a field called the nonce. And the puzzle is you have to find the value of the nonce so that when you take a hash of the transaction data, the value of the nonce is less than a certain value. So you can see here, if the nonce is 673, I take a hash, and I keep doing this until the nonce is less than a certain value. And this value is set by the consensus rules. So each node can individually calculate what this kind of difficulty target is. And when they take a hash of a block, the neighbors send the block, they take a hash, they check, is it less than this value, and then it's valid. And what's important here is because of the properties of the hash function, the only way you could calculate this value of the nonce to find a valid block is you would have to calculate a lot of hash functions. You would have to increment the nonce, take a hash, increment the nonce, take a hash. There's no shortcut. You can only brute force it. So it's very expensive to compute this value, but it's very easy to verify the verify the solution of the puzzle. You just take a single hash to verify it. So it's expensive to compute, but cheap to verify. And this is the important property of a proof of work. And so in a very real sense, this number is a proof that work was done, because the only way to calculate it was to take all of the hash functions. Yeah, and the difficulty adjusts automatically. Each node looks what the difficulty should be, and it looks back in history over the last 2016 blocks and checks were blocks produced very fast or were blocks produced slow, and then it will adjust the expected difficulty so that a new block gets produced on average every 10 minutes. And so what happens if there's a fork? What happens if two miners find a block at the same time? Then the consensus rule is that the longest chain is the valid chain. So two miners find a block at the same time, and then there's a split in the network. And what happens here is the miner just takes the first block that it received and it starts trying to mine on that. And because it's a random process, one of them's going to win. There's either going to be a fork here, or one of them's going to win, and then that was going to be the longest chain. And so this block, this just gets ignored. That block lost the race. It's an orphaned block. Yeah, and that's the rule, is that the longest chain, or more accurately, the chain that has the most accumulated proof of work, which you can think of as really the heaviest chain. Each additional block is adding a little bit of weight to the chain.
Okay, question.
Oh, yeah.
What happens to the transactions which are in the orphan block?
Yeah, that's like a good question. I actually don't exactly know. I think you know the answer? Or? Okay. Oh, really? Okay, yeah. Yeah, and I think most of the time the blocks will have pretty much the same set of transactions.
So wait, what does it mean? No, I'm just curious. What does it mean when it comes back?
It will be calculated again. I don't know.
And then it will be open again?
Yeah, maybe they go back into the pool of unconfirmed transactions, I could imagine. That's probably a good thing to do. Yeah.
You said longest chain. Does that mean that the ones who are kind of solving the calculation need to solve another one, or how is the longest chain created?
So the longest chain is just the chain is extended every single time. So the miners, every time they find a new block, they start building on top of so they find a block, and then this one is now the tip of the chain, and then they all start trying to find a block on the tip of the next, on top of that one. And so the chain just kind of grows. Every time you do a round of the consensus protocol, you find a new block, and you just keep adding blocks on top of the chain, so they're all linked.
The miners actually stop mining, so when they found a new block, then all the miners stop what they do, and they redo the mining.
Yeah, okay.
Look for the next.
Yeah.
Okay, thank you very much.
Okay, sorry. Wasn't super clear.
I have another question.
Yeah.
When you said that it's like technically it's not the longest chain, but it's the chain with the most amount of work, what's the difference?
I think there is in practice no difference,
Basically
but that's
the same
the
thing.
actual official
Yeah.
kind of definition.
Right,
of it
I
at
always
least.
wondered.
Yeah.
I also think it's the
Yeah.
same. Yeah.
It says longest in the white paper, he says as well. So
Okay. Can you explain the relationship between mining and verifying transactions?
it's the same. The miners verify transactions also.
Right. Okay, so I still don't understand when you say they find a new block, what does that mean?
It means they find a solution to the puzzle. The first one that finds a solution to the puzzle, they're kind of all participating in a lottery. The first one that finds a solution to the puzzle wins the lottery, and they receive the right to add a new block to the chain.
Okay, but what is the puzzle? This is verifying transactions.
To find the value of the nonce. Okay, wait, not with the most zeros. You're looking for a hash that's less than. I've lost my slide with the. Here. Yeah, you're looking for. So you have this nonce, and so each miner, they increment the value of the nonce, and then they take a hash, and then they check, is my hash less than a certain value? So the hash is like a 256-bit number. This is SHA-256, and they check, does this hash output to a value less than the difficulty target? And the difficulty target is defined as part of the consensus rules.
So nonce is the number of zeros in the hash?
No, the nonce is just a number, and they try all the different values of the nonce until the output of the hash is less than a certain value.
Okay, so
The hash is, what they hash is...
They hash the block header.
The block?
Yeah.
Yeah.
And the nonce.
Yes, exactly.
So all the transactions plus this nonce, and the nonce changes, and they change the nonce on every iteration. So
So what is the input and where is the output? The input is one hash and one nonce, and the output is one hash.
The input to the hash is the block header, including the nonce, and the output's just the normal output of a hash. And it has to be greater, it has to be less than a certain value, because the output of the hash can be interpreted as a number.
Okay.
What's not clear? Sorry, like.
Yeah. Okay, so there is a transaction verifying part that I cannot match to the hashing part.
This isn't about verifying transactions.
There's no verification.
This is about
here.
finding the next block. This is the process by which we choose which miner gets to add the next block to the chain. Because there's like 6,000 miners and one of them gets the right to add the new block.
Okay, when you add one block to the chain, then you get a coin.
You get some money. Yeah.
Right,
You get rewarded for finding a block. Yeah. And then this thing of like validating the transactions, this is because the block also contains a bunch of transactions. And so you could take a hash of some transactions that are not valid. So they're trying to spend money they don't control, or they're trying to create an input of 10 billion Bitcoins to themselves. And so they also check that all of the data inside of the block is valid. If someone tried to spend somebody else's money and submit that as a block, the nodes would reject it.
So what is in the block is not transactions, it's kind of hashes which are representing value.
No, the block contains transactions.
Transactions.
Yeah.
Okay, so my turn. So it means that the miner have to compete
Yeah.
for the right to validate the block.
For it to add a block.
Okay, to add the block.
They all validate the block.
Exactly. So, and then within the block, the next step would be to validate the transactions within the block. Is that correct?
When if I'm a miner and I'm mining and then I receive a new block, someone says, "Hey, I found a block," and they send me a block, then I check it to see if it's valid.
Okay. First step to compete to
Yeah.
for the right to get
Yeah.
to add the block, and then next one is to validate on the transactions
Yeah,
within the block.
because they're here. There is no like central server. They're all just distributed globally. And so when I find a block, the miner just sends it to its neighbors, and then this miner checks if it's valid, and then it will send it to its neighbors. And then this kind of process proceeds until the block has propagated all the way through the network.
Okay, thank you.
Forgive me for my ignorance,
Of course.
but since there is no any central organization of these things, where do these blocks of riddles comes from? I
Where do
mean,
the blocks with?
the things that you need to solve,
I don't understand.
the puzzles, riddles, where
The puzzles, yeah. So the puzzle is defined as part of the protocol, and the puzzle is always the same puzzle. For every block, it's the same puzzle. But because the data contained in each block is different, there's a different solution to the puzzle for each block.
But in which frequency is this created? I mean, just happen after trade, or it just there?
So every time you find a new block, you start a new round. So every time a new valid block is found, then you start working on a new puzzle.
Sorry, who finds the blocks?
The miners are all finding the blocks. So there's all of the miners in the network. They are looking for the blocks. There's many different miners, and they're all independently looking to find valid blocks.
Okay.
To explain a little bit, basically there's a very difficult calculation, and all these computers are computing for that thing, and it's going to take about 10 minutes, and it's going to change every time. It's always going to be the difficulty for it to be 10 minutes. So in every 10 minutes, another block is created, and within that block, you have, the transactions, basically.
I mean, somebody solves something, and then you have anyone. Okay.
I think there is another one back here.
Maybe unimportant, but so if I'm a miner, how do I know that somebody has solved the block?
So
It's a huge network. I mean, 10 minutes is a short time.
it takes like 1 or 2 seconds for transactions or blocks to propagate across the network. It's pretty fast, and because it takes 10 minutes. But it's actually it's a concern. If you shorten the amount of time it takes, if you made the puzzle easier, then you would have more and more orphaned blocks because they wouldn't necessarily go across the network all the time. Yep.
Okay, so if I'm the miner, how do I know where to get the new unconfirmed transaction to get the right to add it to the
So
block?
the transactions just come from the users of the network, and the users of the network they send it in the same process. They have a few IP addresses of their peers in the network, and they say, okay, I want to send money, and they send a transaction to their peers, and then they send it to their neighbors, and then they send it to their neighbors, and the transactions just propagate across. So every miner has its own stored copy of all of the unconfirmed transactions.
Okay, can anyone be the miner?
Yeah, anyone.
Then how can I see it? Where? And how can I see those unconfirmed transactions?
Because when you join the network, there's a few kind of bootstrapping IP addresses that are in the Bitcoin client. And so first of all, you talk to them and you say to them, hey, I'm joining the network. Please give me a list of all of your neighbors. And then you have a list of their neighbors. And then you just send it to the neighbors. And then when they receive that transaction, they broadcast it to their neighbors. And then these ones broadcast it to their neighbors. It's this kind of gossip protocol. So the transactions just kind of flow out across the network.
What kind of network is that? I mean, how? I mean, how can I start? For example, if sorry for so many questions. Yeah, can you maybe demonstrate on the internet? Do you have internet? How can, for example, I want to be a miner. How can I start? I'm sorry.
I mean, no. If you want to start to be a miner, I don't have it installed on my laptop.
Where do I
here.
go? For example, good website. For example.
You start. You just download Bitcoin onto your laptop. You start it up, and you say Bitcoin D -- mine or something, and then you're mining. You won't find blocks, but you're still mining. You're still working, of course. Like.
Okay. Thank you.
Okay. Okay, so why should the miners bother? Why should the miners participate in this? It's because they have a reward. Because it's expensive to do all of this hashing, to find the solution to these puzzles. And this is implemented as the first transaction in every block is called the Coinbase transaction. And so this is a special kind of transaction that has no inputs, but it has an output. And so here the miners receive a reward from two sources. The first is that when Bitcoin is first created, okay, there's this fixed number of coins, 21 million coins, but not all of those coins were distributed in the beginning. So the miners can take a certain proportion of these unowned or unassigned coins, and they assign them to themselves with this output transaction. So there's 21 million in total. In the beginning, there was 0, and the way that new coins come into circulation is through the process of mining. And the other thing is with transaction fees. So when you send a transaction, there's no kind of explicit fee field, but if the total value of the outputs is less than the total value of the inputs, then this is also, the miners can take this and put this in this Coinbase transaction and pay themselves. And what's powerful about this is because the miner's reward is then linked to this specific fork of the chain. So they're incentivized not just to participate in mining, they're also incentivized to keep the existing longest chain as the longest chain into the future. Because if this changed and the longest chain changed and it was no longer the longest chain, they would have lost their block reward. They would have lost their reward. And so they all want to keep the current longest chain as the longest chain. And because they're incentivized to keep the current chain as the longest chain, if you want to change history, if you want to replace a transaction or change a block, first, if you changed it, you would invalidate all of the blocks on top of it. So you would have to kind of branch off and make a malicious fork. And then in order for your fork to become the new, accepted truth, you would have to make this the longest chain. And because everybody else is working on the existing longest chain and they're going to stay on that because this is where all their money is, you then have to control more than half of the computational power in the network. Otherwise, your chain is never going to grow faster than the longest chain. It'll never catch up. And then, so that's it. That's kind of the base of the security model, or the security assumptions of Bitcoin. But it's not perfect, like anything. There are also kind of problems. And okay, so the first attack is like a 51% attack. If you have more than half of the hash power, that's it. The network's over. It's pretty much, you can do anything. You can double spend. You could just say no one can send any money. If someone had a lot of Bitcoins, you could blackmail them and say, I'm not going to let you spend any money unless you pay me 10 million euros or something. So that's whatever. It's kind of known and it's pretty clear, but there are also ways to attack the network if you have less than half of the hash power. And so the first thing you can do is you can double spend. And so this would look like, here I'm a malicious attacker and I want to get a DVD from Amazon. And so the first thing I prepare 2 transactions. I prepare a good transaction that's sending the money to Amazon, and then I prepare a malicious transaction which is then sending that money to myself. And so first of all, I just broadcast it into the network, and this is like a honest transaction, and then I have the film, and Amazon has the money. But then the next thing I do is I send this malicious transaction, and I put this in a block, and I start mining on like a malicious chain. So I by myself, just start working on this block. And because the process is random, even though I have less than half of the hash power, I still have like a chance to find the block. You know, if I have 20% of the hash power, I have a 20% chance to find the next block. So it can happen that I find the block and I force a fork. And in this point, kind of nobody has the Bitcoins, but I still have the film. And so then one of two things happen. The first, again, I have a 20% chance. So I have a 20% chance to find the next block. And then my chain is the longest chain. And the chain where I sent the money to Amazon, this is gone. This chain is an orphaned, it's an orphaned block. Or the other thing that happens is, okay, the next block found is found on the existing longest chain. And then in this case, Amazon has the money and I have the film. And the chances of this happening are low, but they're like not non-negligible. And there's a risk that you would lose the block reward, and so you're going to cost you some money to do this. But if the value of the transaction is big enough, you could see that this could be a profitable strategy to attack the network like this. And so it's for this reason that people say that you need to wait around 6 blocks deep before the transaction is really confirmed or it's really final. And then if you have 10% of the hash power, you have like a 0.01% chance of being able to carry out this double spend attack. And there's also variants of the attack where if you know the address beforehand, then you can pre-mine a block, and then this increases your chances of being able to double spend. The next one, it's called like selfish mining, and this isn't so much like a attack on the network. This is a way in which miners can take more profit. They can take more than their fair share of profit. And this looks like this. So I have a malicious miner and an honest, everybody else, basically the honest miners, and we're all working on a block. And then the malicious miner finds a block, and then instead of broadcasting out to the network, they keep it to themselves, and then they start working on a private chain, their kind of secret private chain on top of this block. And then maybe they find another one, and so this can just continue. They can keep building their private chain, and at some point, the honest miner is going to find a block, and then they both broadcast at the same time. But because the malicious miner found their private longest chain, even though there's 3 blocks found, the malicious miner has forced everybody else to kind of waste their work, because the work that went into this honest block is wasted because this is an orphan block now. And so in doing this, despite having found 3 blocks being found in total, the malicious miner has 100% of the rewards. And so this way, the malicious miner, if you do the statistics, this works out as a profitable strategy. And the other thing is, the malicious miner finds 1 block, and then the honest miner finds a block straight away, then you have a race, and then someone's going to win the race, but you still have a chance, even then, of not losing your block reward. So even though sometimes you're going to lose a block, you win enough times, and you change your share in such a way that it's still profitable to do this. The final attack is not like an attack in terms of being able to kind of take more money, but it's attack of like a censorship attack. So if I had more than 50% of the hash power in the network, then I could just say, if Bob sends a transaction to the network, I really don't like Bob, and he's not allowed to spend any money on the network. And so if I see a single block that contains a transaction from Bob, I'm going to fork off, and then my chain is going to be the longest chain because I have most of the hash power, and so Bob can never send money in the network. And okay, that's fine if you have a 51%, but even if you have less than 51%, you can still carry out a similar attack called feather forking, and here you announce that if I see a transaction from Bob, I'm going to fork off, and I'm going to keep working on my private fork for a certain number of blocks. So if Bob's transaction gets a few blocks deep, then okay, I'm going to give up. And again, most of the time, this is not going to work. But because it's a random process, sometimes it's going to succeed. So if you have 20% of the hash power, it's a 4% chance to find 2 blocks. And because of this, because sometimes you'll succeed, and the amount of times that you'll succeed is not negligible, the other miners know that if they include a transaction from Bob, there's a risk that their transaction is not going to be included. And this makes including transactions from Bob like a less profitable strategy. And so then even just by threatening to fork, you can kind of incentivize everyone to not include any transactions from Bob. And so this kind of thing of feather forking is, I think, quite interesting because you can have a similar effect of a 51%, or at least theoretically you have this effect of being able to censor transactions with a much smaller proportion of the hash power. So these two attacks of like especially selfish mining and kind of feather forking, they're kind of interesting, and they're these attacks on the kind of the game theoretical layer. And so, but actually there's been no kind of known instances of these attacks. And I think it's also kind of a little bit interesting to see, even though there's all of this research that kind of finds these attacks, like what are the limits of these sort of analysis? And so why haven't we seen these attacks? Even though it would be profitable, like definitely for the miners to do it. First, it's probably just hard to write software, to deploy it, especially if you think you have to convince all of the other honest miners to deploy software that would like deny Bob's transaction. Or, you know, there's like just not enough, we haven't found attackers who are sufficiently motivated, or maybe there's just much easier ways to attack, like, I don't know, hacking an exchange. Miners might support Bitcoin, maybe there's like social costs. If I announce that I'm gonna censor transactions, there's also kind of a social cost to this. And so probably this idea of like economic rationality does not capture the full range of motivations that people have when they participate in Bitcoin. But it does mean that Bitcoin's not completely kind of incentive compatible. It's not the most profitable strategy to follow the rules of the protocol, actually. If you want to know more about this, and there's way more different kind of potential attacks against Bitcoin. Bitcoin's like very robust, it's like really good, but it's obviously got weaknesses. The first is this talk from this guy called Max Fang at bPace. I'll put the slides online so you can see it later. And the other one is there's this very nice paper called A Survey on Security and Privacy Issues in Bitcoin, which is a kind of a survey of all of the different potential attacks that are known at this point on Bitcoin. Yeah, finally, like just a couple of like actual examples of real-world failures when the Bitcoin network was not like had downtime basically. When I researched, I found two. So the first was in 2010. Someone made a transaction that looks like this, and if you see here, there's these two amounts, and these are actually like 92 billion, which is obviously more than the total number of Bitcoins in existence, and it's also the same value of max int. So this is when you have these two transactions and you add them together, then it overflows and you have a negative number. And there was a check for the total amount on like that the total output wasn't more than the number of Bitcoins on the total amount, but that didn't trigger because it overflowed. And there was a check that it wasn't negative on the individual transactions, but not on the complete output. So it kind of snuck through the checks, and then someone made a transaction where they'd given themselves 92 billion Bitcoins. And then the solution was to release a new version of the software that rejected this transaction, and then this is kind of just going back to before because this block was not valid, and so it kind of forked off from before. But there was 54 block kind of accidental hard fork. I'm not sure if it's a hard or a soft fork. Anyway, accidental fork in 2010, and the other case was in 2013, where in a pretty similar way, when from version 0.7 to version 0.8, there was an upgrade from using BerkeleyDB to using LevelDB. And BerkeleyDB kind of had some rules that you could only have blocks that included not more than 5,000 transaction inputs in the block, and LevelDB did not have this limitation. So once clients upgraded to 0.8, which had LevelDB, they could make blocks with more than 5,000 inputs, which were not considered valid by the previous version of the software. So 60% of the network was on the new version of the software, which could mine on this chain with the new more than 5,000 input blocks, and 40% is on this chain on the old fork. This is a question?
Perfect. That's a simple question. Who provides the software that you just talked about?
There's a group called Bitcoin Core, right? The most widely used Bitcoin implementation. But there's a few also different implementations.
I mean, is it company?
No, it's an open source project.
It's what?
An open source project.
Okay.
Yeah. Sorry if that wasn't clear. Yeah, anyway, and so we had again this kind of accidental hard fork, and the solution was that one of the big mining pool owners downgraded back to 0.7. So the 0.7 chain was previously the minority chain. It became the majority chain. 0.8 could also mine on 0.7. So after a while, the 0.7 chain becomes the longest chain, and the fork is resolved. But this was a 24-block fork, which is like 6 hours of downtime of the network as well. Okay. Questions? Yeah. Yeah.
Hi, so I've seen something recently about malware that can take over hashing power from different devices, computers, home computers. What's the possibility that an attack like that could be launched if you were to put enough malware on computers to get enough percentage of the network?
I think that would be quite difficult, especially certainly for Bitcoin, because you can't mine just on a CPU. You have to mine with like very specialized hardware. It's called like an ASIC. And you need like a lot of computers. Like right now, to at least buy all of the computers to run a 51% attack is like billions of dollars.
But even a 20% attack?
Yeah, I mean, there's a risk, sure. I think against Bitcoin, not from just like malware that just goes onto random devices, because you really need this very specialized hardware. Like if I was mining Bitcoin now on my computer, I could look for solutions to the puzzle, but my computer's not fast enough. It really must be this very specialized hardware. The currency that people generally mine with this malware is this one called Monero, which has an algorithm that is specifically designed to be easy to mine on CPUs. But yeah, no, I mean, I don't know how much computational power you'd get like that. Like even the people who mine Monero on websites, I don't think they get more than 10 or 20 euros.
Okay, thank you.
Yeah.
Is mining Bitcoin profitable for anybody at the minute? Like immediately profitable?
Yeah, I think so. I think I saw something that if the price even goes down to $8,000, it's still profitable for the miners. But the miners are making a lot of money, definitely. Yeah.
How many miners are there?
I don't know the exact numbers. I mean, the miners in general, they tend to group into these mining pools as well. So there's like, yeah, I don't know the exact number of individual miners.
Surely that could mean they could achieve over the 50% hashing power if the mining pool was big enough.
Yeah, definitely. There was once in like 2013, one of the mining pools got more than half of the hash power, Ghash, and it lasted like a day, and then the pool split kind of for the good of the network. But yeah, it's a problem. Miner centralization is a problem. I think also for these like attacks, it's a problem.
And if the network's decentralized, how would you enforce that not happening again?
You don't. Okay. It's just expensive to do. But there's a question at the back already. No.
Since the proof of work before was a bit unclear or hard to understand, if it helps people, I could try to give an own explanation of it.
Sure,
if people want that.
Yeah.
Can you go back to the slide where you had it? Yeah. So my explanation I try to mostly give is like the hashing function, you have like a left side and a right side to it. And the left side is all the data contained in the block, which you can see like in the black part. And the right side, the output is the hash, which you can see on the right side. And if there was no criteria or no difficulty, then it would be very easy to mine a block. So everything you would do is you put all the data on the left side inside the hashing function, and you get the hash on the right side, and then you can just add the block to the blockchain. But because there is the difficulty, which says the hash has to fulfill a certain criteria, so the hash is the output on the right side, because of that, the block cannot be added immediately. And in order to change that hash, which is the output on the right side, to fulfill the criteria, which is, for example, start with 5 zeros or start with 8 zeros, there's the nonce, which is on the left side part of the input. And so what you have to do is you have to change your input to get a different output, but you don't know how to change your input. And that's why the nonce, this number on the left side, is something you have to increase or you have to iterate through. So in order to change your output, the right side, the hash, you increase your nonce by 1. And then you get a different hash. But the hash doesn't fulfill your criteria of like starting with 5 zeros. And then you do the same process again. You increase your nonce, and you run the hashing function, and then you get
Yes,
some output on the right side. And you do that process all over again. You increase your nonce, you change the input data, and you get a different hash. And that's basically what the proof of work is. And you have to do this whole process many times until you get a correct hash. I'm not sure if that helped people, but yeah, maybe.
There's another question here. Thank you.
Thanks.
I think my laptop actually ran out of battery, so.
So I was wondering, like, when you said, like, basically that the only actors in this system that are relevant for consensus are the miners. I was wondering if I think that that's correct. I think there's basically like full nodes that are not mining, for example, also somehow participate in the consensus. For example, like they validate. So, yeah, basically the question is, yeah, what do you think? What is the function of, for example, full nodes?
I think the nodes help enforce the rules of the consensus protocol to some degree by being able to validate transactions. But I mean, they're not actively participate in choosing what is the next block. But yeah, it's also blurry. What is the line? Where is validation? This is also part of the consensus rules. It's true.
Right. Like, I mean, like they can validate a transaction. Like they can, for example, reject a transaction not added to the mempool that they store. But on the other hand, like they can also like reject a block. Correct? Like they can not propagate a block further.
Yeah, totally.
So in that sense, they can also like reject a miner's work.
Yeah.
So
no, it's true.
In this sense, yeah.
Thanks for the great presentation. Do you know how like all the miners agree on the current set of unconfirmed transactions to work on? Because
they don't need to agree.
Because it's a continuous thing. It's all the transactions are always incoming.
But they have their own independent pool. They don't need to agree on what is the set of unconfirmed transactions. They just need to have enough transactions to put into a block. It's not important that they agree. They could have completely different transactions. In the end, they have the same set pretty much because it's the same thing. They broadcast it to their neighbors, who broadcast it to their neighbors, who broadcast it to their neighbors.
Right.
So it propagates across like this. But it's not important. They could all have different.
Because the hash will change. The thing is, at least they have to agree on the same set, even if it's differently ordered. Otherwise, the hash would change, right?
The set of unconfirmed transactions?
Yeah.
Why? Why do they have to agree?
I mean, if they're calculating, if the block is some kind of a hash of all the unconfirmed transactions.
The block is only a hash of the transactions in that block. Sorry, maybe that wasn't clear. So that you just take you include you take from the unconfirmed transactions just a small subset, and then you put these in a block, and then you take a hash of this subset of transactions.
Right. And the nodes need not agree on what set goes into your block.
It's just whoever solves the puzzle the first, whoever finds the first valid proof of work gets to choose the valid block.
Okay, thanks.
I think proof of work is not sustainable because it's not environmentally friendly. You need a lot of computing power. That means you need a lot of energy. And I think we are moving toward a green economy. So do you think what is the better alternative? I mean, for me, proof of stake is not good either because it put the power in the hands of only few people. And I heard of proof of importance. Do you know of that? And
no, I don't know.
Okay.
I think proof of stake is probably quite interesting, but at some point, you have to make some trade-offs, probably. Yeah, I mean, you trade electricity for security and you get a lot back. Whether it's worth it is kind of up to us as the users of the network to decide. Yeah, I think proof of stake seems quite promising. Also, proof of storage, maybe. We will see.
Okay, yeah, thank you.
Like to get back to your point, like one interesting thing is that so miners have complete freedom in how they choose which transactions to put in a block. Normally they would choose, let's say rationally, they would choose the ones that have the highest fee. Yeah, but they don't have to. So yeah, they have a lot of power, for example, like he said, to censor a transaction for whatever reason, or to see that a transaction is trying to be confirmed and they can, let's say, replace it because they think it's economically useful for them. So in this sense, yeah, they do have complete freedom, which has drawbacks.
So what it means that if two, so what it actually means is that if two miners come up with a block, it may look completely different.
Yes.
Ah, okay.
Mostly not, because like you said, they'll mostly
Yeah,
always
yeah.
pick the ones with the highest fee, but yeah,
got
totally.
it.
Yeah.
Oh, thanks.
Okay, thank you. So.